Pharmacology is defined as the branch of medicine concerned with the uses, effects, and modes of action of drugs. Drugs need to bind the target to carry out their effects. Unfortunately, drugs have side effects. Many of them are caused by the binding of a drug to its target in parts of the body where we would actually not want the drug to act. Optopharmacology sorts out this issue by using light. Allows having the active drug wherever you want.
In my research, I'm applying optopharmacology to treat Parkinson's disease. Parkinson is a neurodegenerative disease that causes motor symptoms due to the lack of dopamine in the striatum. The most popular treatment uses the dopamine precursor, L-DOPA, to compensate the lack of dopamine. Unfortunately, after a few years, the treatment becomes less effective. Recently, it's been demonstrated that this therapy can be improved by blocking a receptor called A2A. The problem is that this receptor is expressed in other parts of the body we are not interested in blocking too. So, what can optopharmacology do for us? We design a photoactive drug that blocks the receptor only when irradiated with light. So, let's see how it works.
The first step is to try the compound on cells. We seed cells that express the A2A receptor, and we add the photoactive drug. Cells are then irradiated using light of a specific wavelength. This light activates the drug compound. Therefore, the A2A receptor is blocked only in the wells we desire. Later on, the effect is analyzed using a microplate reader. In the second step, we test the compound on healthy animals. Blocking the receptor is expected to induce an increment in locomotion. So, mice are first surgically implanted with an optic fiber. Then, after receiving the photoactive drug, they are connected to the light source. The one who received light moves more. Finally, in the last step, we test it on a Parkinson mouse model. These animals show neurodegeneration like human patients, but only in the right hemisphere. Because the degeneration is only on one side, when an anti-Parkinsonian drug is given, the animals turn contralaterally to the lesion. Similar to the previous step, we implant an optic fiber into the injured hemisphere, and we test for effects of the photoactive drug. Again, only the animal irradiated turns. Will the photoactive drugs be the future in pharmacology? The answer is in the research.